that's what often we post at the time. But hopefully the idea is that it benefits you guys as we talk through it, okay? So we're going to start off with something, shoot, this isn't signed. Okay.
So you don't ask again for 30 days?
It doesn't matter on these computers.
What, really?
No, it doesn't say that. It doesn't
Oh,
say
the
that.
university ones? That's...
Any of the ILE stations, it's.
Oh, they don't?
after
Oh, yeah, I
the
thought that
panel
was your
installed.
actual.
They will actually keep the panel installed, but you notice here it's back to the tour again. They keep reformatting this because they're running into problems with it saving video. So.
It's annoying.
All right, so we're going to talk about the second segment of models, but in order to do so, no audio detected. Stop. Record. Audio. Is that one better? Okay. Okay, sorry. In order to discuss some of the elements that are going to be necessary to think about what we're getting from these models, we're going to have to think about the idea of classification and regression as probabilistic assessments. So in some ways, everything that we're doing here with regard to the neural network processes is a mechanism of distilling frequency analytics from the data sets we're starting with. Now, why I say frequency is because at its most basic level, probability is how frequently a particular event or a particular element from the system occurs. So if we think about something from a pattern recognition standpoint, let's abstract just a moment and think about the idea of frequency with regard to our idea of useful information in the world. So if we roll our heads back a little ways, and we think about the idea that AI, and most of what we consider machine learning systems, are inheriting from biological structures. Biological structures are formulaically, right? So we say that we're not just wired for pattern recognition, we are structurally predisposed to it. The idea being that horizontal and vertical lines, right, are actually the first things that get picked out within the region of the brain that processes visual information. Why would that be the case? Why would we think horizontal and vertical lines would be kind of the most primitive structure to be able to take into consideration? Well, because they have the highest frequency within the system, right? Things either sort of grow up or grow out. You've got horizontal axes in trees, right? So those are the primitives of the natural universe. Structurally, in an effect, those are linear operations, right? If we compose those linear operations, we say the degree of verticality to the degree of horizontal, right? We have a rotation off axis. We have a limb coming out of the tree at an angle. That's going to be another type of edge or linearity to detect. By that process, we compose more complex structures as a result of the integration of smaller high-frequency elements within the system. What I mean by that is faces, right? So humans are predisposed to find faces. Virtually at birth, children began looking to and turning their heads and focusing on faces. What's the purpose of that? Well, if you wanted to learn language, right, you'd probably be in a position where our ears face such that we pick up audio best binaurally with respect to facing the target, and you want to be able to see the mouth formation, right, the shape that the mouth is taking on in order to be able to form those words. So the process of finding faces, locking in on faces, and then sort of watching the expressions, mouth movements, eye movements, etc., is a mechanism by which we learn to reproduce the patterns of the adult. So that the adult does certain things, we replicate, we mirror those processes in our own mind. Which elements are most important with regard to sort of locking in on those facial structures? 2 eyes, a nose, and a mouth, right? In this oval. So we have a series of ovals and circles. So we would say that with frequency characteristics, with regard to faces in general, the structural dynamics and mechanics are related to probabilistic assessments. You could see a circle with two spots in it, right? Misaligned in such a way as to be off axis of the oval, and we would say that isn't a face, right? Versus a certain alignment with a certain frequency characteristics in place of how likely it is for eyes to be close together, right? Eyes to be far apart, eyes to potentially be slightly misaligned but not totally out of alignment, right? They say that a slight amount of asymmetry is actually attractive, right? People that are perfectly symmetrical are kind of weird. They hit that uncanny valley, right? But high symmetry is considered to be attractive. Why? Because it fits our understanding of pattern characteristics, right? It appeals to us. It sort of saturates that portion of our system that goes, yeah, I like that. That's ordered, right? We like order. Why do we like order? Why are we predisposed to that concept of ordering things around us? It's actually a survival instinct aspect, preservation. In order to create something that is guaranteed, right? Security of persistence of availability of resources has to do with imposing order on the world such that the elements become consistent. So previously, we used to hunt animals that migrated. We got sick of that because it wasn't consistent enough, so what did we start doing? We started raising our own animals inside of confined environments. So humans' natural instinct is to impose structured order on things. And it is because of the fact that we see a correlation between what we're doing in the outcome of the process and the likelihood of that particular output resolving to the desired case. So I say that that is, in effect, a probabilistic expectation. All right? So the first item we have here is this notion of probability mass function, discretized versions of natural probabilistic space. Assignment of random variables relative to a unit area, unit space, in which the likelihood is represented as a quantification in columnar form, right? So we have a column that indicates the number of events relative to all events that fell underneath of that designation with respect to the RV. Everybody familiar with this notation, right? If you're not, my hope is we're just going to go through it real quick. If you find something here you go, I'm not super comfortable with, then it'll give you a chance to catch up again, right? We often talk about something called normalization. Now, what is normalization? Have you guys heard of it within machine learning? So the interesting part about normalization is for a specific sample or for a specific set of events, there may be a difference in range of upper and lower limits of the amplitude of a specific signal. The prime example is that audio, because it is collected from a variety of different sources, right, can have varying degrees of intensity. Right now I'm projecting pretty heavily in order to make sure everybody can hear me. And so the microphone that's up in the camera there is picking up, my projection and secondary resonance and all those other elements to it. If I was talking real quiet, I may still be saying the same thing, same information is present, but because it's recorded at a different amplitude or a different volume, then those two signals would look different from one another. Primarily because the range of values, the upper and lower bins of the discretizing characteristics, are going to need to be compared apples to apples, right? We're going to have to create a projection of natural probability space for the discretization of the values such that it fits within a uniform probability mass function for all samples within the set. Okay, so this is going a little bit even beyond what we talk about in just sort of strict applied probability in providing analytics for the output. What we're going to do is we're going to take the system, we're going to quantify the characteristics of it, we're going to then project a stable distribution from that probability mass function and utilize it in order to create consistency across all samples. So normalized audio, if you normalize audio, you can temporally normalize it, such that if you're listening to a song that's relatively quiet and the next song in your playlist starts off with a real loud guitar solo, right? You don't want to go, wake up real quick like that. So what you might do is you might turn on normalized audio. What is that going to do? Keep a small amount of the derivative of the change in amplitude characteristics from the previous song as you push into the next song, right? It's going to smooth the transition by requiring that the audio amplitude of the next track abides by the same relative level of output. So we say that audio is normalized because it has been placed within the appropriate upper and lower quantity gaps of the entire range of the values. Interestingly enough, normalization can be accomplished in several different ways within neural networks, right, and deep learning in general. Sometimes normalization is going to happen on an individual sample level, right? You might want to normalize it such that all the values fit within a certain domain for the full range, right? Or you might want to normalize across a group of samples, which we call batch normalization. Or you might want to normalize for the entire system. So normalization across the entire data set, that's sort of like a bulk normalization process. We often utilize that as a pre-processing directive. But in some cases, right, so let's make, for instance, an example here, and that is an extension of what we've been talking about, which makes neural networks relatively different than many of the other modeling techniques that we've taken into consideration. And that is, neural networks can be deployed on real-time data. Most of the time, we're used to doing what? Go collect the data, bring it back, and then train it offline. You guys remember that terminology, offline training? Right? It's not active, it's not being trained as it's currently operating, it's being trained in the background. Now, what's the reason why we do that? Is because we can make inferences based upon the distributional characteristics of the data that's presented, and we can be able to use things like the mean of the distributions for both the inputs and the outputs, and create normalizations for them based upon their empirical differences between the expectation of that value and the range of the output values. Structurally, if I have a new sample that's being collected in real time, so for instance, I was running what would be called an adaptive system. Now this class used to be called neural networks and adaptive systems. We've talked about the concept of backpropagation for a singular sample in order to try to optimize the weights such that the error is minimized for the sample. We can expand that up to groups of samples for batches. We can expand that up for whole runs, whole epochs, running through every single value, every single sample in the data set, right? And we can choose when we're going to backprop, and we can choose what segment of it we're going to normalize for. Each of those has advantages and disadvantages. We'll talk about some of them as we go through. But I want to phrase it or frame it with respect to these traditional equations that we're used to dealing with, because once you sort of understand that, you'll know why you needed to know it up to this point in time, right? So collectively, we have the uniform probability distribution, right? In this particular case is an example of equally likely K classes in a particular system. Now, what I mean by equal likelihood, typically, in this particular circumstance, would be if I have two classes, I would say that those two classes happen with the same frequency characteristics as often as one another, but with respect to separate assignments of the random variables, different outcomes, okay? So a coin is flipped, has uniform probability, it has likelihood of falling heads or falling tails. Now, is it perfectly heads and perfectly tails? Some recent mathematical examples, right, which include, I believe, 100,000 manual coin flips with recording, all right, indicate that there is a slight bias toward head on the American quarter, all right? Why we did that, I have no idea. Okay, there was some budget left over somewhere. We had to figure out something for the TAs to do. You know, if any of you are TAs or research assistants, and you're feeling like your data processing is tedious, imagine flipping a coin over and over again all day and hitting heads and tails button in the system, all right? Yeah. Okay. So just trying to remind you, you know, it's like the guy who had no shoes until he saw the man who had no feet kind of perspective, okay? So density functions can further be extrapolated or be expanded on such that for all x in some system of members of set x, right, the probability of x for some system must be greater than or equal to 0. This is what we call the non-negativity theorem. Non-negativity implies that for a whole system, right, if an event can occur, there's no such thing as an event that has negative probability, and at very worst, it just didn't occur experimentally. Now, when we're talking about probabilities within machine learning, we're not usually talking about fixed discrete probabilities with theoretical outcomes and calculable theoretical outcomes. Rolling dice with calculable theoretical outcomes and fixed format solutions doesn't usually apply to something that we would use machine learning for, right? That would be like trying to, as I've mentioned beforehand, trying to swat a mosquito with a nuclear weapon, okay? It's just overkill for the particular problem. So we're going to only use this in the particular case of circumstances where we're collecting data from the natural world, all right? We're observing experimental process. A lot of what we do actually is kind of experimental process. We're going to formulate some expectation or some correlate between elements, and then we're going to create a functional understanding of it. If the probability of a value within a system is equal to 0, that effectively means that the event did not occur within our data set. Does it mean that event cannot occur? No, it does not mean it cannot occur. But track with me for a second. If within our data set, that particular event did not occur, and the probability of it is calculated sort of statistical deviation equal to 0, what is the likelihood that our model is going to be able to compensate if that event does occur at some point in the future? Very little, right? How in the world can it compensate for something it either never saw previously or has a calculated expectation of 0 with respect to the previous understanding? This is part of that problem that has been discussed for those of you who've done ISL, right, and applied probability, for that construct where you say, if it does in fact converge towards 0, that means the frequency of that figure or that particular outcome of the system, of the event, that class output, if you want to look at it from that perspective, was not observed. Thus, all the weights for it are effectively set to 0, right? You could think of weights within the system as being approximations or understanding of the likelihood of occurrence and the significance of the features for that particular class that lead to that output in this particular case. So the summation for all these systems is ultimately going to be a multivariate uniform distribution such that we can either think about the finite summation or the indefinite summation of multiple outcomes in the system always equaling to 1, total probability space. Total probability space as it is recognized here would be what? All samples, right? It's all outcomes with respect to all samples. So what we've sampled is going to give us the information we're learning from. Whenever we do computing with marginal probabilities related to summational rules, right? We think about for all x such that x is a member of set x, the probability of x relating to being a member of a specific class or specific subset of x would be equal to what? All the probabilities of x, assignment x, for all particular variable outcome operations y. Now this is the given operator in some senses because we're going to construct our understanding based upon pairing. This is once again that idea of linking together the input and output for relational expectations. We said previously we utilize the softmax layer in order to approximate a version of this system. If we do it for probabilities of potentially infinite variables, right, infinite assignments, which the natural system is analog and thus has values that can occur in any value in the space, we're going to have to use an integration rather than an indefinite summation. However, what's the likelihood of actually incurring this within computing spaces? Computing spaces are discrete, effectively, right? So what we're actually going to do is we're going to take the continuous world and we're going to project it into some form of concrete aspects, right? The idea of classification is the process by which we take indefinite, fuzzy natural world with smooth continuity and transform it into finite structural continuity. Conditional probability implies what? Sequential computation. Condition implies that I now know something based upon some previous set of information. Now, how do we use this within neural networks? We actually have the concept of Bayesian theorem within neural networks, right? Where we can say the conditions or the update of the output of the system can be supplied, right? We can say, give me estimated probability based upon the inputs, and the system can learn what the spaces are and the relative frequency of components therein, and can return the probability of a class from effectively 0 to 1. Interesting. What function do we utilize for that? Softmax is one of them, but if we just thought about it as a strict activation, the sigmoid operation would be really good at it, right? Because its range of output is from 0 to 1. So if we're looking at a strict probabilistic operation, and we just want to know the likelihood of convergence between two events, right? What's the likelihood of A, given that B has already occurred? We can now calculate that likelihood as an area-driven summation. What I'm actually applying to there also is that temporally defined networks may have to utilize conditional probabilities and sequential outputs as well. Let me explain to you what I'm talking about here. So we start off with the chain rule of probabilities relative to the probability for assignment in any given number of particular class outputs in the system, such that the assignment of a unique specific probability for a specific class is going to be returned as a vector. This is where we were talking about with the softmax, right? So you have n number of classes to assign. You're going to get, by running through this function, n number of likelihoods of the class of the output of the system. I'm getting up to something that is going to be interesting with this. I just want to make sure we're all up with notation as we're walking through it here. If I wanted to do something like take a sequence of words, okay? How many of you have taken the natural language processing class, NLP? We have 3, okay? This is actually a relatively difficult task. It's funny because it seems like, ChatGPT and all that stuff does it like this, right? Well, I would say that it also is a massively over-parameterized network for that particular task. But it ultimately boils down to this. This is the interesting part of it. In that, if I was to think about the probability of the sequence occurring, right? Some probability of sequence, I could look at it as the relationship of the probability of word 1 through word t within the system occurring. I could decompose that into the probability of word 1 and word 2, right, with respect to word 1. So now we have the intersection of those systems with respect to the likelihood of the first word case, right? I'm compacting this. Normally I would say probability of word 2 given probability word 1, or word 2 given word 1, right? And I could ultimately continue to expand this such that the probability of some word t at the end of the system relative to the previous given relationships all the way up to t minus 1 would be what? Sequential. So it says that if I have the word it's, my, right? What happens? What's the next word there? Google's been doing this for a long time. Go up to your Google and start typing in. Remember autocomplete?
Yeah.
Okay, I remember when that was not a feature of the internet. And whenever it started happening, what is that? We had large corpuses of data, and it says that according to the frequency calculations, if I have word 1, word 2, word 3, etc., I'm going to take the likelihood frequency of that word to occur relative to the second word to follow it, right, with respect to the first word's occurrence frequency within the system. So, given word 1, what is the likelihood that the sequence will be word 1, word 2, is returned as a probability function. Which word do you pick? Now notice something. ChatGPT does a really good job of it, but whenever I'm punching in on my phone, you get that little, you start typing a word, right? Or you swipe a word if you're a swiper, right? What do you get across the top when you let off?
Other suggestions after you type? Yeah.
Yeah, what are they? When we're talking about this, what are those suggestions that are at the top?
Top 3.
They're top ranked, right?
Top
So they're
ranked.
ranked. Okay? So they're the top rank with respect to the likelihood of the outcome of the system. So how many words did we look through there? We only looked through the words that we've been given thus far. And there is a functional maximum amount of memory that we can keep track of in order to be able to constrain and contain the sequence of all the words that have come up thus far within the system. So this becomes conditional sequential chain probability for likelihoods. What are those numbers at the end of this sequence? A small number times a small number times another small number times another small number. Even the top 3 ranked things are going to be tiny decimals, right? Tiny, tiny decimals. So the funny part about this is it's actually similar to the construct of backpropagation, because products of small values creating smaller values has an issue toward the end, where long chains of sequences of likelihoods and assessments of likelihoods based upon density will result in values that are almost so small as to be negligible. But we're still going to have to take the top ones with respect to the performance. Okay, so if any of you are wondering how this cycles in, NLP and any other sequential, predictive sequential algorithm is going to use probability-based analytics in order to both keep track of the relevant information as well as to shorten the sequence, or to keep only information within maybe the last 5 to 7 items relative to the element of the last piece of the sequence T, right? So WT at the end of this is the last word in the sequence. So rather than keeping all the way from 1 through T minus 1, we might have T minus 5, T minus 4, T minus 3, T minus 2, T minus 1 as the supports. That is the information that are providing us with the likelihood estimate. Because truthfully, does the first word in the sentence have a big correlate on the likelihood of the next word in selection? No, we usually can narrow the scope. And once again, that is driven by an understanding of the frequency of those specific words within natural language space. Some languages are better at this than others. English happens to be relatively well predisposed to it because we typically tend to put modifiers, right, and then targets. Whereas some other language that create targets then modifiers can create a little bit of ambiguity with respect to next likelihood placement relative to frequency and within comparison to individual frameworks. Imagine this being trained for you specifically, right, relative to it being trained for someone else. Is that a different dynamic? But it would share some of the same conditional underlying properties, right? We call the process of taking one model that might be trained on unified information initially, that would be a model that's trained on everybody's texts and entry frequency and large corpuses of data, right? And then a model that is taken from that and modified to be personally preferential to you. The process is called transfer learning, all right? We'll talk about transfer learning again elsewhere, but there's actually some notional characteristics that definitely apply to frequency-driven analytics, because if your cadence of words, if the direction of your speech and the vernacular you use, right? I use big words. I don't know why, it's just the way my brain works, okay? So I go looking for my brain goes looking for the exact right best words, or at least I try to in my mind. Now sometimes it creates a little bit of extra complexity for people listening to me, but at the same time, it corresponds to what? Higher informational density. So higher informational density lets me get more concept out within the same unit time. My frequency analytics are going to be a lot different than a 13-year-old girl texting, okay? Which is probably going to be 90% an emoji for some reason of late. Like, they actually said recently that teens are actually constructing whole regions of their brain now that refer to emoji. that aren't related to strict language structure.
Yikes.
So they're even training some neural networks to be able to work with and be compatible with questions asked and output provided with text enhanced with emoji. It means the emoji, no, this is true. Ask ChatGPT something in emoji. It can do it. Now don't ask it right now. It lost its mind last week somehow. I'm not sure why. Okay, but we'll talk about that. We're going to talk about some of the reason why some of these models lose their mind.
I thought the short ones were difficult. Now the emoji.
Yeah, emoji, right? That's it.
Oh my
And you
God.
add subjective interpretation, right? But at the same time, isn't it just a token? Isn't a word just a token?
Yeah.
Right? So emojis are also just tokens. So frequency utilization characteristics of the token, which in truth are they're ASCII type characters, right? They have code sequences to them, so they're already tokenized. So they really were easy to learn with because they were already structurally tokenized. Their co-frequency with words is also utilized. Is a dictionary ever brought into play when teaching ChatGPT? No. It doesn't have any concept of what the words mean. It's only interested whether or not their frequency characteristics are co-associated. So part of the reason why I'm harping on this is that we're utilizing some of these same mechanics in order to train even modern methodologies, all right? Conditional independent and just strict independent events, right? Independent events occur such that they're simple product relationships, and conditional events occur such that the outcomes are changed in some procedural fashion. What's the secondary characteristic here of import with the idea of dependent events? That the sample space has actually been changed for event B relative to the occurrence of event A. So this means that this has a partial relationship to one another, right? So the value of B occurring totally within the system is going to be partially dependent on the frequency of A occurring, right? As well as the independent frequency of B occurring, non-sequential to A. So now we have two potential outcomes within our system. We have B can occur, potentially could occur without A, right? We have a probability of B. That is the area that takes up. We have the probability of A, and then we have the probability of ordered operations, right? The change in A relative to B, the change in B relative to A, looking at the intersection from both sides of the system. So our functional analytics are going to have to take into consideration that, hey, if I see feature A, that means that there is a change in the likelihood of B. So I may actually have to make an adjustment to my expectation that the next word in the system will be such and such word, word 3, right? Based upon word 1 pushing forward and changing the structure of word 2, changing that frequency analytics. So it's constantly shifting what is admissible based upon the pre-sequential elements of the system. So this is the reason why you actually need a dynamic analytic, reason why the system has to be able to have more weights than just strict linear interpolations with one another, right? These are not strict linear representations. We see that nonlinearity being applied here, most common nonlinearity being applied here is going to be natural expectation, right? So expectation from the system, right? Variance and covariance respective to, everybody's seen these, okay? I'm just going to go forward. Respective to the underlying distribution of the normal Gaussian, okay? As I said previously, our understanding of the normal distribution is a tenuous one, right? We have a little bit of an understanding to it. But if I were to tell you that most information theory talks about that expectations, variance, and standard deviation of a distribution are really the only things that we need analytically in order to make predictive capacity on it. Empirical theorem says 99.7% of the data representative of any given natural normal distribution should be within 3 standard deviations of the op. 95% of it, right, will be within 2 standard deviations, and 68% of it will be within 1 standard deviation. So, what happens to this? We said previously that trying to find novel examples or trying to find useful additional information from distributional material, right, is from take the data and determine where the edges of frequentism lie, right, the upper and lower bands, something like height of an individual, right? Very few individuals are greater than this 3 standard deviations away, right? But we have a 0.3% chance of being, 6'9" and above or something like that, right? This actually also implies something that's a bit problematic for us, in that with all information presented, we're going to get most of our samples within that very narrow area right around the outside of the mean value as provided by our standard calculations. This also means that there's going to be a bias towards center, right? There's going to be a bias towards center. We're going to be pulled in to the middle simply by the frequency of the events having occurred here. So the model is going to prefer values and prefer systems and is going to conform to the capacity to successfully identify and successfully correlate the features of the system with the outputs, mostly within the band of the highest likelihood values, highest likelihood assessments. So this means that if you're in more of an edge case space, your model is going to not actually have the greatest capacity. Partially this is also related to the idea of which features to use. So if we say that we have 5 features or 10 features within a system, if 68% of the values can be appropriately classified using 3 of those values, but the remainder of them, up to that 99.7%, require us to go up to 10 values to accurately classify. We're going to have some cases that are going to be very easy to figure out with very simple models. And then the remainder of the cases, in order to make the model more robust, is going to require us to take a broader scope about the features at play. So we could say, in general, the things that are closer to the mean are going to be easier to identify and discriminate with fewer pieces of information because they're likely to lie further away from any other secondary comparison of the distributional mechanics. And then things that are going to fall further out from the distribution are going to require us to make more assumptions. We're going to have more model complexity in order to correctly or cumulatively analyze the underlying aspects of the system. So any discriminant that gets put in place in this system is going to have to take into consideration the total value for systematic expectations. All right, covariance and precision characteristics of the system. What is a covariance? That is things changing relative to one another. If I have 2 features of a system and I have them varying with respect to one another, then that means that there may be data represented twice within the system. The example that I give, an example that I typically talk about, is the idea of barometric pressure and relative humidity and temperature. Since they all vary with one another, barometric pressure is technically a derivative factor based upon how much total dissolved moisture in the air at a specific temperature point, right? So if I use all 3 of those features, I'm technically going to be counting some of the variational data more than once. By doing so, I place additional significance on that feature within the system. So that additional significance that I'm placing on that system needs to be ordinally adjusted for with respect to an understanding of the covariance of the system. If we have highly covariant components, we are going to have to make sure that we eliminate those that do not perform well within a system. They can be confusers. Okay? Precision matrices also are based upon natural expectations or natural expansions of normal distributions for secondary characteristics of the coefficients, right? So the precision matrix will apply both the capacity of that specific system to provide the desirable class given a systematic constraint or a loss function or cost function. So we get specific outcomes from that system based upon how well it can characterize the target classes within the space. Okay. Distributions that we often utilize in these cases, right? We have exponential, we have the Laplace distribution, which is an expansion on frequency cases, right? So we said frequency was the key factor that we were interested in. So we're going to utilize the Laplace transform in order to be able to make an understanding of the natural expansion of likelihood in the system. The Laplace transform also allows us to be able to expand on the eigendecomposition of the Hessian matrix of that second grad, J, right? The second gradient of the values for expectation of the errors in the system, so our distributions. Dirac function is what? That is just instantaneous form, right? That is just a discriminant that says across some point I have an instantaneous change in value. Mixture distributions, everybody remember these?
Yeah.
Okay, so if I have three Gaussians, these each represent the distributional characteristics of three classes. Notice they're well separated in this case, except for whenever you get close to the base of the system. So having three well separated classes is probably ideal because we only need two discriminants in order to be able to create a reliable understanding of the space, right? We only need two surfaces that will compartmentalize those three classes. So K minus 1 surfaces in order to be able to create reasonable discrimination for output. Now with regression outputs, right, we only talked about those initially with regard to the idea of utilizing mean squared error expectation. For something like classification output in Gaussian mixture space, we use cross entropy, which I think we talked about briefly as the categorical metric that we're likely to be using to put out later on. Now, when we're looking to assess a model, we're going to assess it whether or not it provides consistent performance between training and testing, right? We're also going to look at it as how well it provides classification performance in the case of multi-class data, utilizing something like the AUC of a receiver operating characteristic, or in some cases we'll use the combinatoric matrix of the confusion matrix, right? We use accuracy, precision, recall, F1, F2 score. If you're not up on that mechanism or that score assessment methodology, then I'll have to provide you with some additional materials. But how we assess a model likely falls underneath of those two categories, either regression, right, quantitative characteristics or qualitative characteristics. Those qualitative characteristics are mostly related to the probabilistic functions underlying that spatial distribution. So how does this spatial distribution get learned by the model? Because it's only seeing perhaps one or two samples at any given time, right, or maybe 10, a small batch of them at a given time, randomly selected from that grouping. It's going to have to be an iterative process by which it tries to continue to move the discriminant surfaces in the space based upon the nonlinearity of trying to find optimal decision surfaces dividing each of these multiple Gaussian outputs, okay? So we're going to use estimators, probability estimators for something like the logistic function operation, right, which we've called our sigmoid operator, or something like the soft plus or soft max operator in order to determine cumulative likelihood for the outputs, okay? Bayes' rule, this is an expansion of our natural understanding of likelihood relative to cofrequency, and if we change the variables for the expansion function, we can rewrite the probability of something like dy dx for gx, right? So the probability of x given x for dx in the system of a full partial, right? Says partial differential here would be p of x for gx, decompose it into partial of g of x relative to x, and the probability of g of x. So any linear operation that's applied here, technically this is a convolution because it's an operation on another function. We can decompose it as partial relationships. Once again, what does this look like? The backprop methodology, right? The partial is that the weight or likelihood of a specific weight having an implication on the system relative to a class output could also be categorized as its partial of function, or the distinction or the distinguishing of that particular activation function relative to class likelihood distributions. Okay, so this is going to utilize the matrix format for the determinant of the matrix composed by the element-wise operations of g of x and x for the given probability space. Okay, so that's just jij relative to x of ij relative to y of j, right? Each of the partial of x relative to y. This is decomposition, once again, given here operating as g of x on x. Information theory says that an event provides some amount of useful power of distinction or discrimination of that sample relative to class output, such that we have negative log p of x for a given 2-bit system, right? So it's just a sample will give you a modification of log likelihood for that distribution relative to the total discriminant space. Shannon's entropy states that if we decompose h of x for that system space, we can get negative e of x for probability p, right, the subset p, such that log p of x becomes a determinant operation as well, right? Log p of x in this case is an array expanded for output convergence. So if we say that two systems of information characterized with one another, one provides us with the capacity to be able to model such that we can easily differentiate between the two classes, and the other data set is very difficult to be able to distinguish between the two classes. We might say that the relative entropy of the set which is difficult to distinguish between is lower. Now, the reason why I say that the entropy is lower in the second set that's difficult to distinguish between is if all values represented in the original set are technically possible, but not present within the second system, that means the subset in the second system is in fact informationally deficient and would be seen to not contain adequate information in order to be able to provide the described or expected output in this particular case. So we said that if the sigmoid operator utilizes the linearity of the natural expression E, natural exponential, then the log likelihood, or log p of x, is the inverse of that proportion, which would be the remainder likelihood of that particular value. So if a sample provides you with the capacity to be able to further describe the space, then it's adding information. Entropy says that the quality of a data set is related to how well it describes all possibilities and is evenly distributed, or at least as well distributed throughout all of those possibilities as could be expected, especially as it relates to something like the normal distribution. This implies what? What is natural entropy? What do we think of as entropy, right? Everything is gradually tending towards disorder. So a high entropy data set would have also, in a weird way, high informational value because the data is spread out, representative of, and appropriately dense with respect to the assumed underlying distribution of the system. So the continued convergence of the entropy system would be that as that particular representation, as that particular data set converges towards the true representation of the underlying system, then we can expect a improvement, a consistent improvement in the outcomes. Okay. I'm not going to talk about the rest of the, we'll talk about directed model for just a second. Any of you guys ever heard of graph theory? Mm-hmm. Okay, so within graph theory, the implication of a probabilistic system can be represented similarly to the way in which we have weighted connectivity between nodes in a neural network. So directed node systems, such as those that might happen in a Markov chain, are a representation of quantified probabilities, quantified likelihoods of observed state transitions for this particular case. So things like large networks of connections between computers are expressed in graphs. Who you connect with on Facebook and who you often follow, what things you're likely to buy, where you drive to and from, and trust me, they're taking consideration of that with your GPS, are listed as these directed structural graphs, all right, where the weights and the likelihoods of changing from state to state in the system are provided by as frequency functions. How often, out of how many circumstances, are you going to move from one connected state to another connected state? And that becomes an informational characteristic such that the structure or the topology of this system implies the degree to which it adequately describes what's happening underneath the hood. So we don't necessarily need a strict feed-forward neural network in order to be able to describe to us the sequence of likely events. We can express it as a sequence of connected directed elements within a graph using probabilistic procedural outcomes. But how do we decide upon those? How do we train those systems? We have to figure out how many nodes we have, that's how many unique states and operations, and we're going to have to determine the transitions between them based upon observations. We're going to have potentially hundreds of thousands or even millions of observations in order to be able to ascertain what those connectivities look like in order to make meaningful understandings of them. Most language systems for likelihood transitions can be expressed in this way. When we're thinking about one word to the next word, we see sort of divergences of likelihood for that word leading into the next word, and then connectivities of that word into all subsequent words within a string of sequences. So depending on how deep you want to go in order to make this representation, you can build further and further graphs from this. So there are metagraphs that discover the whole space, and then subgraphs that work with individual segments, right, where we're inheriting and moving on through elements of the system. Okay, so let's go to the second part of our zoo, all right? And I want to talk to you guys about the first of something that, this is all the zoo stuff is stuff that we're going to talk about basically for the remainder of the semester. I'm still not done with backprop and auto optimization, but I'm trying to do that in parallel. Trust me, it's a work in progress at the moment. And we're going to look real quick at the IPMB, I think, for the code that we're going to utilize as part of the first of your projects. Okay, so I want to go through this at least one or two examples here. Quickly talk about the items that are coming up. Anybody ever seen these generative adversarial networks? Okay, they're what was utilized before what would be called standard stable diffusion now. Okay, so generative adversarial networks still have a lot of utility because they provide us with the capacity to be able to take two sets of information, right? One, which is a set of real samples, right? These are samples sourced from the natural world, and samples generated by some forward methodology. Now, interestingly enough, we start off with real images, right, to train both the generator and the discriminator, and then we're going to split this model up. Now, why did I want to talk about probability first? Because each of these real space values, along with knowing that they are real, right, categorizes for us that there are certain features in common amongst real samples that distinguish them from fake. So if you think about it this way, what's the likelihood of a fake bill to come through a bank?
Pretty low.
Pretty low, right? Most of the time that stuff's kept out of the bank. But what happens if one does come in? Do we train the people that work in the bank with fake money? Nope. They never see fake money, interestingly enough. They only train on real money when they're doing the training process. This is an interesting relationship, and it's actually kind of funny because the discriminators work similarly. They are trained only to be able to identify real images, and the assessment is what? Fake images should have a slight deviation from the procedural characteristics of the real image such that they should be discernible. Fake money has a different feel, right? feels different, it's weighted different, folds differently, sounds different. If you've done nothing but hold real money your whole time, and you're starting to sort through money and you go, what the crap is this? You know, you're like, that's not money. You don't need the support of fakes in order to tell real. The interesting portion of this is that we have two people operating here, right? We have the art forger, right? And we have the art critic here, the guy that assesses the value of the art, right? All he's seen is all the real, real artists for a long time. And then this guy comes down here and tries to produce for you a new output in the style of, Dali or Picasso or Monet or something like that, right? And the discriminator goes, nah, missed it. But what we actually do is we feed back the elements that the discriminator decided were the deciding factors, right? It says, this is fake, and I can tell you why. Right? It says, here, right? These things are wrong. And the discriminator goes, cool, I'll be back in a minute. It updates its understanding of what it needs to do in order to try to make something that fits better in the distributional mechanics of the actual real distribution space. So this is a system that's attempting to fit to a probability distribution that the original discriminator was trained on, right? And it's attempting to learn from its mistakes. So the update process for something like generative adversarial network, which is a high-level type network, is going to utilize that propagation of expectations from the system. So we're going to look at we'll look later on at how exactly it makes some of those determinacies, and whether it's an image or whether it's a sequence generator, right? Some of these can be written such that you have not just like a convolutional network for image output, but something like the ability to write sentences or make statements, all right? So before some of the bigger pre-trained transformer systems, we had these methodologies to take into consideration, all right? Long-term, short-term memory systems. Like I said, this is just a look ahead at where we're going to be going for some of these subsystems. LSTMs are a little bit outmoded, and they've been outmoded by transformers because their original intention was to keep only a small portion of the original information, right, concurrent to last sequence within the cycle. Pretty complex looking, right? They are structurally complex. The methodology by which information is added to the external memory, right, that implies a significance and carries over that information to the next sequence of the recurrent. And there's multiple different operators here. We have hyperbolic tangent and sigmoidal operators, as well as biasing characteristics. But the output at each layer relative to hidden state operation are going to be informational to C of t, right, with respect to C of t minus 1. So the output of the cell is going to be given h of t output for hidden value, right, and next hidden state update, as well as the activation operation for this sequence of the network based upon the current state. So each layer activation, right, the whole network feeds into the next version of the network. So each one is modularized. You can think about it as a sequence of each of these networks feeding on to the next one in the system. Technically, this is just the same network, right, taking in some of its own outputs from its previous system and keeping track of some of the elements it thought were most important to the relative update. This was actually originally invented to tackle that vanishing gradient problem, and we'll continue to talk about that as we go forward. All right, so these are really cool techniques that allow you to be able to analyze sequential data in meaningful ways. So LSTMs were around before we started with structural, something that was called Muppets, all right, and then Muppets were pushed into transformers, all right. What are transformers? I'm showing you this mostly to give you an appreciation for the fact that as you get up into some of the more advanced stuff in this topic, it starts to get really hairy, okay? There's a lot of workflow going on here, a lot of movement. But many of the elements that are happening in these cases are additive noise, pairwise positioning operations, and operational outputs such as linearities and softmaxes. ultimately at the end of most of these systems, you have positional encoding operations, embedding operations for state, and then what's called multi-attention states. So multi-attention heads and masked multi-attention heads. Many modules can be placed in parallel within this system, which is an advantage of the transformer, which means that some aspects of the performance of sequential analysis can happen in parallel, which was a huge necessity whenever we were describing and designing systems that could work with book-length texts, right? How do you keep track of what happened in the previous chapter of a book when you're making an analysis of a story going through that whole space? The answer is you don't yet, right? The answer is it still is very difficult to get something that can read a book and keep track of the characters. Especially it's difficult to get something to write a chapter of a book, right? And then utilizing the information from the previous chapter of the book that it wrote, make a new portion of the story. If you've ever noticed, many of the things that are being output right now, you guys see the text to video processor, right? Notice it only makes like 1 minute long videos. Why? Doesn't it make videos any longer than that? Because what's happening is that over time, it begins to gradually lose its mind, okay? It will not know how to keep track of the previous semantic information. So transformers are an attempt to try to fix that, but they don't totally fix it because they can't have enough functional side memory in order to be able to truly resolve all of it. And they're still functionally beholden to that problem where low frequency elements, here's the key factor. Low frequency elements, right? Mention a character one time in a story and what do we do with it? We go, oh yeah, I remember that guy from 2 chapters ago. What happens if a specific character is really low frequency in the system? What happens to its probability? Near 0 for that to be accounted for again, right? Because it's so low frequency in comparison to the other elements. Keeping track of elements that have incredibly low frequency, what happens to the transformer with regard to the side memory? It forgets him, right? It forgets her. It forgets the character off to the side because it says, I haven't heard about them in a while. I don't need to keep track of them. So we still need to incorporate some form of archival lookup long-term memory in conjunction with these systems. And these transformers are being integrated into even larger systems that inherit that capacity to be able to keep track of information in a much longer-term perspective. All right, from here we're going to go and probably this will be about the closure of all the topics we're going to talk about in the whole class. This is looking forward to kind of the second module where we really get into the meat of the deep learning structures. But we might have a few other items I throw in there like reinforcement learning, etc. Okay, thank you guys. I'll see you guys on Thursday. I probably don't actually have time for this, but what we'll do is we'll look at it on Thursday. If I get it up and assigned beforehand, then look at it. But I have code here for how to be able to implement your own neural network, and then we're gonna profile the performance of this network, and then we're gonna transition to doing it in TensorFlow with Keras, TensorFlow or PyTorch. I don't care what your implementation is. But then we're gonna get into building the networks with Keras, where we're gonna do it modularly, and we can start to put together some of those bigger models later on. Okay. So we'll start off with this. This is challenging to provide you all of the individual little steps along the way. All right, so I started writing this assignment and I keep going, oh, I need to put more detail on that. I need to put more detail on that, okay? At some point in time, I'm just gonna push it out. I'm just gonna go, okay, figure it out, okay? Do it. So we'll get there. We'll start off with that and maybe try to fill in the details as we go forward, right? Give you some code, give you some data sets to opt from, and then let you play with it and figure it out on your own, all right? All right, talk to you guys soon.